I remember going into factories and we were thinking, oh, how do we make this? And they're looking at us and they're saying, we need this. Like, what you're building, we need this. And we're looking around, and it was like going back in time, like 150 years. It's just, in the way that we would grind people up for food production, we grind them up for other production. And that was striking to me. And it was one of those moments where, so I think we have a lot of ideas, right? We have lots of ideas, but every once in a while it's reversed and the idea has us and it just pulls us. And that's what happened with us, is that we knew that we had a skill set that could really help people. We had a heart for it and a passion for it, and that's why we're here. Hi, I'm Rosanna Myers from Carbon Robotics. I'm one of the co-founders and the CEO, and we build intelligent, low-cost robotic arms for industrial manufacturing. So we build robotic arms that are essentially 10 times cheaper to implement and enable people to automate tasks that traditionally have never been automated before.
What sort of tasks are you able to automate that have not been automated in the past?
So there's a range. A lot of people don't know this, but really most manufacturing today is done by hand. So 90% of all the tasks across manufacturing that could be automated are done by hand. And so these can be really quite simple. They can be things like putting a piece of plastic into another piece of plastic, attaching a wire, inserting screws, tapping a screen to make sure the buttons work. And typically those are done in a single work cell by one person for 8 hours a day, sometimes 12 hours a day, and they just do that same thing repetitively over and over again. And these are things that typically have not been automated for a variety of reasons.
Can you explain some of those reasons? Why have they not been automated in the past?
The biggest issue, first and foremost, is cost. So robotic arms are really expensive. They're expensive to buy initially, so it's easily tens of thousands of dollars for the arm. But that's just a piece of what you're getting. You're not getting the tool that kind of serves the purpose. You're getting one component of a system that you need to implement. So you'll get one company making the arm that might be tens of thousands of dollars. You'll pay maybe another $15,000 for a gripper, so the hand that goes on the end. If you want to incorporate a vision system, that's probably separate again. And then if there's any kind of work cell, and you start adding these things up, and the costs actually start to kind of multiply, because what you're talking about is something that ends up being a massive integration project for an end user. It isn't the case that you've got a tool that just works out of the box and you can say, hey, go put this piece of plastic in another piece of plastic. What you've got is a tool that you can say, go to random coordinate here and that random coordinate and that random coordinate, which means that the pieces aren't reusable. It means that it has to be you really start from scratch every time you want to automate a new line. And one of the biggest, most disempowering pieces of it is that you rely, typically, most manufacturers rely on outside experts who are the only people. They know their task, but they don't know how to automate it. And so they hire in these experts who can take weeks. By the way, in the US, it's 4 to 8 weeks on average for an integration project. And a lot of times the tasks that they're doing actually don't exist for that long. So in contract manufacturing, for instance, the average assembly line now is only 3 to 6 weeks. And so if you're waiting 4 to 8 weeks for a contractor, even if the economics made sense in terms of the upfront capital expense, you just can't automate today.
I'm definitely under stress. So if I seem like I'm not under stress, then I'm going to be clear, I'm definitely under stress.
When we look at the companies using robots in their manufacturing, it's hard to move past Tesla. Tesla has been using robots to help with the production of their electric cars. The idea was that by using automation, you could produce more cars in a far more precise way. But as you may have already heard, they've run into some major production problems.
You said to your team, everybody get ready to meet the demand. We're going to be in production hell.
Yes.
But you didn't expect this kind of production hell, or did you?
No, it's worse than I thought.
Why is that? Why is it harder? What happened?
We got complacent about some of the things that we felt were our core technology. We put too much new technology into the Model 3 all at once. This should have been staged.
The robots, despite being autonomous and very precise, were actually slowing down the production process. They constantly required attention from operators and also needed recalibration. The issues caused huge delays to production and forced Tesla to rethink their reliance on automation.
Elon, part of the thing I heard about the Model 3 is that there's too many robots, that maybe...
Yeah, I agree.
You think so too? That maybe you need more people in here working?
We do.
In some cases, the robots actually slowed the production, right?
Yes, they did. We had this crazy complex network of conveyor belts, and it was not working. So we got rid of that whole thing.
And Rosanna says that Tesla's problems are actually indicative of some of the bigger issues with the current generation of industrial robots.
When you look at the tools that they were actually using to implement, you can see where a lot of the challenges come into play. And this is a company that is making one of the same thing. They're not having to change it change their line every few weeks. They're setting it up. They can spend 6 months, 9 months getting the line together, and then they're just going to make that. And even they have massive problems. And so I'll give you a very specific example. With them, they use a couple of robots. Many of the robots they use are KUKA robots, which is one of the big four big robotic companies. And to program them, you need to know KRL, which is KUKA robot language. It is a proprietary language. It's their own proprietary language, and it's based on Pascal, which is from the 60s. It's a procedural language. It is prior to the concept of object orientation. And anything that you want to do, any of those robots that are in production are using this system. And so when you want to integrate, not only are you putting multiple pieces together, you're working with wildly archaic, outdated software that is just not designed to be up to the standards of what you really want it to do, which is to be flexible. And so that was what they said at Tesla, was that a lot of the delays were from an over-reliance on automation, and that the humans are underrated because they're very flexible. And a piece of that, though, is making production tools more flexible. That's the challenge.
So you think the issue was more about the fact that the tools weren't flexible enough, as opposed to whether or not robots could actually do those jobs?
So mechanically, a robotic arm can do almost everything a human arm can do. The problems that you face are around having it integrate with other parts of a system to be able to actually do that and to be able to react to the real world. So flexibility, you can define it in a few different ways, but when you're setting up a robotic arm, imagine this, when you're setting up a robotic line, the way that you make it easy for a robot to do a task is you make sure you have like heavy fixturing around it. You make sure that a part comes in and it comes in exactly the right space at the right time when you're expecting it. Now, if you have a part coming down an assembly line and it's 3 millimeters off, you might not be able to pick it up depending on what it is. And so what that means is you have to not only build the machine, you have to build the machine for the machine, and it just starts to amplify. And so it really gets down to flexibility, and so all of that can be modeled as cost, but it's that the tools themselves need to be able to react. They need to be able to see what's going on. Robotic arms are dumb and blind. They have no vision systems incorporated. They tend to be running very, very old computers. Like communication bandwidth is typically like 500 hertz. It's not great, and it's not set up for understanding the environment and being able to respond.
Why have these systems not actually been updated to object-oriented languages and to have these sensors and abilities? Because that is something that your company is working on, is giving your robotic arms like the sense that there is a human around it. So can you talk a little bit about that? Like, why has this not happened in the past?
So there's been a lot of siloed development in the past. There are 4 big companies that really ruled robotics for a very long time: FANUC, Yaskawa, ABB, KUKA. And these are companies that are actually set up to be on, let's say, like an automotive assembly line. So the kind of applications that Tesla was setting up, they haven't faced the market forces that would kind of push them into being more flexible. There's some movement towards having it be object-oriented and have new programming languages, but then you've also got backwards compatibility. People buy robots, they expect them to last for over 10 years. And so you need to be able to maintain what's in the field, but then also be able to innovate. And typically they're fundamentally not software companies, like deeply in their core DNA. And let me give you a very specific example of this. So KUKA, I trained at KUKA. You can go to KUKA College. It's in Michigan. It's where you can get KUKA certified. You can also do it in Germany.
They've got their own training course and university. KUKA
certified, yeah. So if you have an error code with your machine, you can't just go online and like your Stack Overflow, like, hey, I've got this error code, what does it mean? You actually have to call them up, like, I'm not making this up, you have to call them up to a person will pick up the phone, normal business operating hours, tell them the code, they look it up in a book, and then they tell you what the issue is. And there's so many things that are just ridiculous about that. One of which is that that's a printed book, right? There is definitely a digital copy. And, there are restaurants that are, in the middle of nowhere that can get a PDF of their menu online. And this has just not been a priority. And so it's just staggering what you have to deal with, and also the expectations are set at that. When you go and speak to people who've been in the industry for 15-20 years, then they don't have the kind of expectations that we have coming from the tech sector. And actually, I think one of the biggest problems is that there's been the companies that build the robots that are typically in that world, and then you've got a lot of really cool R&D happening at universities, maybe it's happening in companies, but there's a big gap between the research that happens that typically is only really needing to work, let's say like 999 times out of 1,000, and that's considered success. That is not success when you go into an assembly line. It's absolutely not. And so you have, oftentimes people are speaking about robots, but they're speaking about them in completely different ways, and they're talking past each other and not listening. And I think fundamentally, one of the big challenges and one of the reasons why there hasn't been this convergence is because there's a lack of communication.
How is your company approaching this problem, and how are you improving these robots?
There's a number of things that we're doing differently, but the overarching goal of what we're building is to make these tools that are incredible production tools, accessible to people who would never be able to typically afford them or to set them up themselves. So we've leveraged really a lot of innovations that have happened with cell phones, with drones, actually like smart washing machines, funnily enough, from Moses, to be able to put it together and to design a robot that does understand that the one is cheaper, but two is more intelligent. So it, as a system, as a full system, it's integrated. So we talked earlier about the issue with needing to integrate multiple pieces of a stack to make a robot do anything. We've flipped it on its head, and we've said, we know that you need to do a task. We know that you need to do certain tasks, and here's all of the things that you're going to need to do those, and we can encode that into the software. We build it into the hardware, and so it's very specifically designed for tasks. So we do a few things differently. One is that we have integrated vision. I think if the robot cannot see what it's doing, where it's going to have some problems. And that has to be built into the hardware itself. A lot of times people think, well, why can't we just build the software or the AI on top of it? And then they realize that there are like fundamental laws of physics that get involved, or the issues around like communication bandwidths not being able to support what people want to do. So you really do sometimes. One of my favorite thinkers, was a pioneer of the robotics industry, Alan Kay of Xerox PARC, who basically invented modern programming and like built half the internet. He said that sometimes when you're really serious about software, you have to build the hardware. If you can build the tools, you probably are better off doing that rather than trying to retrofit what exists. And so we've started from the ground up, and that's fundamentally different. And then we've done, there's some work that we're doing around safety as well.
One of the big issues with robots when used in manufacturing is their safety. Most industrial robots are actually pretty dangerous because they aren't designed to be used around humans. They don't know where humans are located, and they can move rapidly, only stopping when they've actually hit something, and you don't want to be hit by a large robotic arm. But Carbon Robotics is taking a different approach. they're actually creating robots which can sense whether a human is nearby, giving the robot enough time to make sure that it doesn't actually cause harm.
Most robots, traditional industrial robots, have no idea if a person is around or if there's even an obstacle in its way. So if you're going between point A and point B and there's something in the way, it will just drive right through it. And they're powerful. They really can drive right through it. And so what happens is you have to put them in these cages because they have to be, safe. And then you have to figure out how you get stuff into the cage and get stuff out of the cage. And so there's a whole system that builds up around this. And so there's been a move in the last few years, I'd say the last maybe 10 years, towards collaborative robots or cobots. And this is the idea that robots should be safe enough to be around humans and to work side by side. This is the dream, that you've got one person doing a human task and then you've got a robot doing this sort of monotonous task next to it, and it's safe. The main way that collaborative robots today get this safety is through a thing called force sensing. So it's actually what it sounds like in the name. When the robot senses the force of hitting you, it can stop or it can slow down. That's actually too late. That is not when you want the robot to know that you're there. And so what happens is robots are only considered collaborative when they're running at like 20% of their rated speed or less. So they're doing these kind of like yoga moves. And that's served a purpose. There's a lot of applications where that's fine, but you're not seeing the industry hype translate always into adoption on a production line. And so that's a really interesting question. Why is that? And the reason is that what if you care about? If you're a manufacturer, you care about throughput. You care about how many parts you can get out, how good they are, how quickly you can do it. That's how you make money. That is your bread and butter. And so the trade-off between a robot either being collaborative or a production robot is just unacceptable. It's not something that you can realistically try to do. And so when we set out to solve this problem, we looked at it in a couple of ways. But the main was that the robot should know where you are if you're within a certain range from anywhere on the arm itself. And so, yes, you can add in additional sensors, and you can put it in a light cage, put it in a cage, put light curtains, put additional sensors. But most sensors have problems of some description. So you put a vision sensor up, and there's issues with occlusion or minimum sensing distances, cones of view, those sorts of issues that make it not always 100% reliable. And typically they're off the robot; they're not incorporated into the robot. And so what we envisioned was a sensing skin, essentially. So, and this is a sensor that we're building into the housing that can detect humans up to about 20 inches away from any direction from where it is. And so the idea is that you can have a robot. So we have all of the traditional fail-safes of collaborative robots, but we have that ability to predict and then react in time. So what you can do is to have a robot that is running as a production tool in a collaborative fashion. And we've not seen that ever done before.
So it really limits the risk to the human that's working around the robot, which means then you don't need to have all the cages, etc., because the robot will stop as soon as it senses that there's a human in the way.
Right, and it has the time to be able to react. In our mind, this is a major step towards true human-robot collaboration.
And we'll have more of our interview with Carbon Robotics CEO and co-founder Rosanna Myers right after this break. Welcome back to Moonshot. I'm Christopher Lawson, and before the break, we were speaking with Carbon Robotics CEO and co-founder Rosanna Myers about the use of robots in industrial applications. And one of the comments that always comes up when discussing the use of robots in manufacturing is the loss of jobs. Will humans actually lose their jobs? And Rosanna spoke about this ideal situation where robots and humans work side by side in harmony. But is that goal even remotely realistic?
So that's a really, really important question. And I think that one of the things that disappoints me is a lot of times there's there's a discussion that's so polarized, and that's on the one hand it's either super idealistic and everything will be great, and on the other hand it's, oh my gosh, what's coming, I don't know what's coming, and it seems terrible, and there's often not this bridge in between that is a pathway for how things will be. And so it's an issue that we think about a lot. The first thing I would say when it comes to manufacturing is it's important to understand what some of these tasks are that robots are doing, first and foremost, because they're not tasks that you and I would want to do. We'd want somebody that we love to do. They are really subhuman. When we want to make something, when we want to produce things, for all of human history, this is how it's been, we grind up people. There's some underclass typically, and maybe they graduate out and there's a new one, or maybe we move to a place where there's lower cost of labor, but some human, like the 90% of those manufacturing tasks are actually getting really they're really not just monotonous, they're and mind-numbing, they're subhuman tasks. They're not something that anyone would want to do. And so it's important to first just ground ourselves in that reality that the world right now is not great for everyone. It might be great for us sitting here or at a tech conference. You've got a very educated audience. They get to probably pursue their passions and their dreams and to use their intellect. That isn't the case for all of the world. So the first thing is to say, actually, this is not the way society should work. So I think that's the first point. But then the second point is that, okay, so we're going to see this change, and that's good. It's good that humans can move to tasks that are much... the way I think of it is having more humanity, but we don't know what the ratio is going to be. We don't know what is it going to be 1-to-1, and so there is a lot of work to be done around retraining the workforce to be ready for the new economy.
Now, Rosanna recognises that while there will be a large group of people who can retrain to work alongside robots, not everybody will be so lucky. We've already seen an element of many jobs being lost to robots, and she told me that it's this specific issue which has driven Carbon Robotics to adopt an approach to robot design that focuses on the people actually using the robots. If you can make the robots simple enough that operators can easily transition to work with the robots without requiring a specialized skill set that requires a knowledge of 3D space and other specialized coding skills, then you allow more humans to work in this new economy, and make it much easier for companies to transition their manufacturing processes and adopt more efficient technology.
What's the most challenging issue that you still have to solve?
So I would say that for our initial product, we've been able to solve a lot of the technical challenges, which is great. The big push for us right now is to be able to manufacture and to distribute and to build not just 10, but go up to 10,000 and more. And so there's a lot of challenges around just, ironically enough, around manufacturing. And so I think our biggest challenges are with that. And then as a company, it's also finding the right people. I think because of how the industry has been, where you sort of have this academic track or you have this industry track, a lot of times the people that we want are at the nexus of that. So they have the depth to. Our CTO actually puts it the best, I think. He says people who don't just read the book but could write the book. That's the level of depth that we're looking for. But you also need this cross-functional understanding, because if you poke one thing, something else comes out, messes something up. If you change something in the mechanical system, well, there are electrical implications and software implications and controls and all of that. And you have to kind of understand that. And then on top of that, you have to really want to make a product. You have to be really excited about building something that goes to people. And then on top of that, you have to want to work at a small company. And there's just not that many people in the world who fit any of those, really. And so growing the team has been a real point of focus for us. And I'm very happy with where we are now. We've been very specific about hiring, not just for skill set, but for mindset. So we make sure that everyone on the team has this core belief about what we want to do. Because I think no matter where somebody is in an organization, their core priorities and their core passion is going to come through in their contribution. So if they don't really care about the end application and that's not as exciting to them, then that's going to be reflected in the product. And so it's kind of the issue behind the issue is making sure that we really do have the best of the best people, and the best as we define it.
How did you first get into robotics and become interested in pursuing technology?
So I grew up in England and in the countryside, and so I was around a lot of agriculture and production. And from a really early age, I was immersed in like the tools that make, in that case, food, but really that go into what typically we take for granted. So I was really interested in the tools and the processes and the people and the stories, and I had a father who like really encouraged technology to learn about those things. And there were a lot of stories and a lot of pieces. I mean, I remember learning about a combine harvester. Like my father taught me about a combine harvester, and it's this incredible tool. So it's I'll tell you a little about combine harvester. It's a combination of 3 different very groundbreaking tools for harvesting, and it's essentially, when you put them all together, it's like this mini factory on wheels, and it dramatically shifted how we produce food. And it didn't just shift that, it shifted society in the most like unbelievably fundamental way. So I think it was around 97% of people who'd been doing like back-breaking labor, hand tools and working the fields went into other industries. And productive capacity goes up 10x, and so food is cheaper and there's more of it, it's plentiful, and society really grew out of that. And it was a technology that actually was very scary for people because they didn't know what was coming. It's, well, this is different, and what am I going to do? Which makes total sense, right? If you do not know what's coming and you don't know if you have the skills to be okay or the tool set, of course you're going to be afraid. That's actually one of the reasons why we speak very candidly about things, is we want to have that conversation. It's really important that we're talking about it. Even if we don't have all the answers, we should be talking about it, and everyone in the field should. But it was very inspiring for me because it was this tool that came along kind of just the right time and did just the right amount of things. And because it did that, it had this massive impact on society. And so I went to university, went into software development, was building, and I met my co-founder in university, and we were working on this thermoelectric heat exchanger for cooling water. It was very efficient. It was 120 times more efficient. It was like drinking fountains and water coolers, and we had to freaking build this thing, and we could build a couple, we couldn't like build a lot. And so we started looking into like production, and that was the earliest insight into the earliest moments of like, wow, a robotic arm would be great. It can do everything. It's kind of like the PC of robots.
Do you remember the moment when you first realized that actually this could work, that you actually put all the pieces together and something happened and you realized, we're onto something?
Yeah, so it doesn't all come at once. The very first thing we realized was that we could make a robot arm a lot cheaper because we could replace what are traditionally expensive mechanical components with essentially commodity hardware and very clever control software. And we were told by experts flat out at the beginning of the company that it was not possible. We're like, why do you think that? So you should always ask, right? When people say something's not possible, it's like, okay, well, maybe I'm missing something. Maybe we're complete idiots. What do we not know that you know? And the answers were really, really, really disappointing. They were things like, well, based on the price of harmonic drives, max and motors, there's kind of like these components that go into every system. You're going to have to wait for some industry to bring the cost down. It's like, well, that's not exactly a physics-based answer. What you're talking about is your understanding of the supply chain, which is actually quite limited. Because it is possible to, a lot of times, like what we consider to be off the shelf is actually someone else's excess inventory. So you just have to work your way down to figure out what actually goes into making things. And so that was the first moment where we were like, this is crap. Because these are the people who are meant to be leading the industry and, who get a lot of the funding and they're not trying. Like, why? it was staggering for us, and we're like, we think we can do this, and we spent a lot of time very poor, very hungry, very sick in factory floors. We spent a lot of time in Shenzhen. I think I spent 7 months out of the first year of the company in Shenzhen, 10% more, and but we finally got a proof of concept, and it worked, and it was this moment of like, ha. And we actually, as a very small company, we got named to this. There's a Robotics Business Review. There's a list of the 50 most influential robotics companies. And it's usually like Boeing, Amazon, Google, or Alphabet now. And we got on the list as this like 3-person team for doing what we'd done. And it was actually some of the same people who, you know. So that was a moment where we realized that we'd done something important. But I think the bigger piece of it is we've always tried to. I'm a big believer in a beginner's mind. So let's assume that there's something that we don't know, and if we knew that, then we'd be further along, even if we feel very confident in what we know. And that's meant that we've become very good listeners, I think. And so as we've been listening, we've really been co-developing. Our ideas aren't just, oh, this is a random thing that I think would be fun and like scratching an itch. It's, oh, wow, it's like with a safety sensor. That came out of the problem. It was very specifically solving that problem. And of course, it has huge implications for anywhere where you have machinery around people. But it started with very specific wanting to solve that in mind. And so I think that as we've developed more technologies, that feeling of, oh, this is going to work, has been a combination of saying something isn't possible unless it like fundamentally violates the laws of physics, right? Like unless you have to be willing to do a deeper level of exploration. It might not be possible, but you have to be willing to really test it. And then you also have to make sure that what you're trying to solve is the real problem, not just the stated problem or the perceived problem, but it's actually getting into the heart of it. And I think if you do that consistently, then you'll get to those moments of, oh, it's working. Great. That is better than not working.
Where do you hope to be in 5 years, your company? When you look at your company, where do you hope to be in 5 years' time?
So in 5 years, I hope that we've solved many of the core challenges around manufacturing. So it really can be used for production ubiquitously, and that we've really done that we've really solved it so that people... I want to walk into those same factories where it first struck us, just how unequal and unfair life can be. And I want to see them moving forward. I think that's just like personally a very exciting moment. And then I want to see us as soon as possible opening up to developers and really building, not just an application specific device, but something that can become so much more than what we could do. One company can do a lot, but not as much as a whole worldwide community.
Awesome. That's great. And does your robot have a name?
It does. Our robot's called Cassia. It stands for Kick-Ass Trainable Intelligent Arm.
I think that's perfect. Excellent.
Thank you.
Thanks for listening to this episode of Moonshot. If you love what we're doing, then please share the show with your friends. We're available wherever you get podcasts, including the new Google Podcasts app for Android. So make sure you subscribe. Keep tabs on what we're up to by following us on social media. Just search for Moonshot Pod or head across to our website, moonshot.audio. Moonshot is a production of Lawson Media. It's hosted by me, Christopher Lawson, and also Andrew Moon. Our artwork is by Andrew Millist, and our theme music is by Breakmaster Cylinder. That's all for this episode. Join us again next time as we explore more big ideas that are set to change your future.